In this video, we're going to continue learning about how we can use simple calculations to plot new meteorological variables. In this video, we're going to learn about thickness. Hopefully you've had a chance to watch the conceptual video that talks about thickness. It's a very important variable in the atmosphere, especially with regards to estimating what is going to be the precipitation type, i.e. rain or snow. On page 2 of your handout for the technical aspects of this material, we begin talking about thickness, and one of the most common thickness levels is the 1,000 to 500 millibar thickness. And so to do this calculation, we're going to go ahead and start with our model_calculations_thickness file. And so we're going to go ahead and duplicate that. And we are going to put our duplication in our working folder. And then from our model calculations thickness, we're going to go ahead and rename this. And we're going to say thickness_calculation. Once we've got that ready to go, we'll go ahead and open it up. Now, I have not yet used this notebook, so I'm going to have to change the kernel to be Valpo Spring 2020. I'm going to select that. And once that is up there, then we are generally ready to go with our new kernel. And so to start out with, we just need to initially run our first 2 cells here, which are going to be largely similar to what we've done most of this semester. And so what we're doing here is we are gaining access to the GFS data from the thread server, so we've got all of that forecast data available to us. And so when we want to go ahead and do our simple calculation, we know we need to take the difference of the 500 millibar heights and subtract the 1,000 millibar heights. And the reason that it's 500 minus 1,000 is 500 is going to be about midway up in the troposphere, and so there'll always be much greater values, somewhere around 5,500 meters or so. And then 1,000 millibars is really close to the surface, and so that, or even below the surface, and so those will be near the ground. And so this will allow us to have positive values of thickness to be able to determine what the precipitation type might be. And so again, as in a previous video, we're just doing a simple calculation here. It's a simple subtraction. And so that we are selecting from our data set the geopotential_height_isobaric variable using the metpy select method to subset for both time via the plot time, which we defined up here, and choosing a particular vertical level, say 500 millibars. And then we are subtracting from that geopotential height and using metpy to select the same time, just a different vertical level here of 1,000. Now we've wrapped this in outer quote marks to be able to have this difference being over two lines. And we're setting this, the result of this, equal to a new variable within our data set called thickness. And so since we're just doing one time for one vertical level in each one of these variables, should run pretty quickly. And Shift-Enter, sure enough, it does run pretty quickly. And so now we want to go ahead and plot this thickness up. And so we move now on to our cell that is going to do our plotting. And so in this first contour here, we're going to plot from our data set our new variable, thickness. And note here, for our level and our time, we have to choose none. Because we've already subsetted for a level, our new variable, thickness, does not have any level. And so the way we can see this is if we go ahead and look at the metadata for our thickness variable. And so we see our thickness variable only has 2 dimensions, the latitude dimension and the longitude dimension. As a result of that, then we need to set level equal to none and time equal to none so that we can plot this appropriately. Our contour levels here for the 1,000 to 500 millibar thickness is going to continue to use the 60 meter interval that we would commonly use for 500 millibar geopotential heights. That's because this calculation is dominated by the 500 millibar geopotential heights. Now we are going to color our thickness red and plot them in a dashed line. The reason we're using red here is because thickness is basically a surrogate for temperature, as it's the average virtual temperature of the layer between 1000 and 500 millibars. In addition to this thickness plot, we're going to plot geopotential heights for 500 millibars. I've not subset the time, so we need to go ahead and put in plot underscore time in here. And then we're going to contour them at 60 meters and color them black and be solid. And we're going to add both of these to our plot. And we're plotting 1,500 millibar thickness at our plot time, and it's by me. So let's go ahead and give this a run and see what happens. Takes just a minute to run, but there we go. We've got data from February 28th, 2020. And we see we have both contours of thickness in dashed red, 500 millibar heights in solid black. Now, these two variables we often don't plot together. Often it's mean sea level pressure and 1,000 to 500 millibar thickness. But what we're seeing here is that the relationship between warm average temperatures in the layer and cold average temperatures in a layer being related to mid-level atmospheric phenomena. Specifically, when it's warmer than average or higher values of thickness, we see ridging at 500 millibar heights. Where we see lower thickness values, that means we have lower temperature values. That is in areas in which we have troughing. Let's go ahead and rerun this now, but just for a different date. So let's go ahead and choose something closer to current. We're going to choose March 26th at 12 UTC. And so we'll have to rerun that cell first to grab access to our data. Then we're going to calculate our new data. We can get rid of this next cell now by cutting it out since we don't need to see what the data looks like anymore. And then we can go ahead and rerun our cell and see a slightly different picture because it is a vastly different date, almost a month later. But we still see the same thing where we have colder temperatures, we have lower thickness values, and then lower heights at 500 millibars. I hope this has helped unlock just a little bit of the mystery of thickness, but more importantly, how simple it is to calculate the thickness variable and add it to a plot. Thanks for watching.